Hi, year 11s and 12s. Look, in this video, it's a little bit different. We're doing this one at school rather than doing it at home with the computer. So it's the office this time. No microphone, no fancy camera. But the point of this video today is to go through how to write up a practical report for biology. Now, this one's going to be targeted for a Stage 2 practical report. If you're watching this for a Stage 1 report, everything's mostly the same, except you've got 1,000 word count for this. So we've got two different files up here. We've got the task sheet for the completion practical, which is the effect of changing enzyme concentration on lipase activity. And we've also got an actual practical report from a student a year or so ago that got an A. This is for the deconstruction practical that you will see later on in the year. But this is how to write up a prac to get a similar mark. Now, truthfully, this student was probably borderline A+. You can see there's 4 A+, and an A and an A-. So truthfully, they're very close to an A+, so this is a good one to look at for this. Now, I won't go through the task sheet for the completion practical, so if you want to know how the completion practical works, there's a separate video on that, which will be linked at the end of this video that you can watch, or you can find that on Doing Science Right. But the first thing we'll address is, so the first thing you always should have in your practical is you should have an effective title. So here we've got the effect of different concentrations of glucose on the anaerobic respiration of yeast. Okay, so that title tells me exactly what we're looking at in the practical, connects the variables together. It's everything we need in a title. The next thing which is important is it's got the word count. Okay, so for Stage 2 biology, the word count is 1,500 words. For Stage 1 biology, that word count is 1,000 words. So in the word count, you've got include your introduction. So in your introduction, that's your aim, your background information, your hypothesis, and your variables. So that's independent, dependent, and controlled variables. All of that's part of the introduction, so all of that's included in the word count. Your analysis of your results, the evaluation of your method and the procedure, as well as the conclusion. All of that is included in the word count. So that means that your method, your apparatus, your safety and ethics, your results, those sections don't actually count to the word count. So don't need to worry about them when we're looking for the 1,500 words, but the other sections do. Now, remembering that Stage 2 biology is online submission, so that means the word count is very easily checked, so you don't want to lie about the word count. You want to make sure you're hitting those 1,500 words, or a little bit under, to show that you can be concise, but effective in your prac write-up. So what we're actually looking at here is, this is the page we're going to focus most on here. This is how to write up the prac write-up, and these are the different components of what should be included in your prac write-up. So first off is your aim, so we'll just scroll down to the student's aim. You can see my comments on the side as well. Okay, so an aim should be written in the correct format, so it should never start with, the aim of this experiment is to. You should never start with that. It should always be something like to investigate or to observe or something like that. So as you can see the way the student's done this, to investigate the effect of different percentage concentrations of glucose on the anaerobic respiration of yeast by measuring the amount of carbon dioxide released through water displacement. Okay, so in this, he's written in the correct format. Okay, he's indicated the purpose of the experiment, and he's also connected the independent and dependent variables, and that's really important. Okay, so the independent variable is the one that he's changing. That's the different percentage concentrations of glucose, and the dependent variable is what he's measuring, the amount of CO2 released through water displacement. He's used the independent and dependent variable in that aim, and also detailed exactly what the experiment is looking at. Okay, he then moves on to the background information. Now, this student probably had a little bit too much wording for his background information, probably looking around 250-300 words for your background information. Okay, it needs to be information that's relevant to the practical. It's information that's going to help you explain your results later on. If it's something that's not to do with the experiment, so say you were looking at enzyme concentration, you're not going to talk about how changing substrate concentration is going to affect the experiment, because that's not what you're looking at. You're focusing purely on the aspects that are going to be relevant to your practical. Okay, it should all be related back to the aim. Okay, and it should be helping you. This information that you're putting in the background information should be helping you to formulate a hypothesis or an educated guess of what the results are going to look like in the next step. Okay, so looking at 250-300 words, including diagrams is a great way, as long as you're referring to the diagrams, like the student has. So he's set up here, as seen in figure 2, and then he's included figure 2. Just putting a diagram there and not referring to it that doesn't count. That's pointless. You need to be referencing the diagrams that you have in there. But then once you've done your background information, you're moving down to your hypothesis. Now your hypothesis should always be written in the correct format, so that's not in the form of a question. And again, that should be linking your independent and dependent variables. It's important that you have if, then, and because. So you're explaining why you're predicting this. So again, we'll read this student's example. As the amount of glucose increases, so that's the if, the amount of carbon dioxide produced because of anaerobic resting will increase at a decreasing rate until a plateau is reached. Increasing the amount of glucose will increase the rate of enzyme-substrate complex formation, therefore more carbon dioxide will be produced. At this point, the student has talked about if, then, and he has started to mention the because there as well. So the because there is always relating back to the information and the background information. So if this happens in the experiment, then this will happen because of what I've researched in the background information. Okay. With your variables, you need independent variable, dependent variable, as well as controlled variables. For your independent and dependent variable, it's enough to just state them, but you also need to provide that little bit of extra information. So for your independent variable, you need to state what you're physically changing. So this student here, the independent variable he stated is the glucose concentration, and he's then gone ahead and listed the different concentrations that he's going to be using. Okay, for the dependent variable, he stated what the dependent variable is, the amount of carbon dioxide produced, and he's also talked about how it's going to be measured. So in this case, via water displacement in a 50 milliliter measuring cylinder. So independent dependent variable, you just state those variables, and then you physically talk about what you need to be, how you're changing the independent variable, or what you're measuring the dependent variable with. So in summary, for the independent and dependent variable, stating what the independent variable is, and how you're changing the dependent variable, stating what the dependent variable is, and how you're measuring that. Sorry, we've had a bit of a room change, but still the same video. For controlled variables, that's a little bit different. You don't have to use a table. Now, just quickly to talk about a misconception. Just because you include something in a table does not mean it's no longer part of the word count. So if you put your controlled variables in a table, that's still part of the word count. Okay, I would strongly suggest putting your controlled variables into a table like this here. But what I would include is you have your variable. So what is the controlled variable? Why you need to control the variable. So what will happen if you don't control the variable? And how it's physically kept. How did you control it in your experiment? So for this one, we'll look at one example. The students kept the amount of yeast used in the experiment controlled, because if they used different amount of yeast, it would alter the number of enzymes present, which would make the reaction occur at faster pace. Okay, they kept it constant by making sure they used 200 ml of the yeast suspension every time. Okay, that's how you do a control. You should always have at least 4 controlled variables. So you can see they have got 4. If your word count allows, it's also nice to sometimes think about doing a little table for uncontrolled variables. So things that you've tried to control, but just physically weren't able to control. What you've done to reduce the effect of that uncontrolled variable, as well as what it's going to do to the data. That just helps with your discussion a little bit later on. Okay. We then get to our apparatus. Now, apparatus is a really easy step, but a lot of students get it wrong. Now, the main thing that you need to be doing is you want to make sure you're listing absolutely everything that you're including in the experiment, with the quantity of using. So for example, you've got 1 water bath here, and the extra details. So this water bath was held at 35 degrees Celsius. Okay, or over here we've got 1 50 ml measuring cylinder. I haven't just written measuring cylinder, we've written how many are there and the exact size of it. You need to have all that information so that whoever's doing your experiment, from what you've written, can replicate your results identically because you've provided all the relevant information. Don't have to do that one as a table. A lot of students do. I'm fine with it. As long as it's a list, that's good. Okay, list or table, both perfectly fine. The method is, again, a really easy step, and a lot of people do the method wrong. Okay, so as we go here, the method is telling us how the independent variable has changed, describes how the dependent variable is going to be measured. It's got every step that you've done in the experiment. It's numbered, and it's written in past tense and third person. These are all really important. Okay, so a great way to describe how to write a method is think about you're writing up this experiment that you're about to do or that you have done, and you're going to give this to your grandma who's never studied science before, and just reading your method and your apparatus list, she can follow your experiment exactly as you've done it, and ideally get exactly the same result. So your practical is replicable from the information you're providing. Okay, so past tense third person, so all materials and apparatus were placed in the center of the workbench. Refer to diagram 1.1 to ensure all material and apparatus have been retrieved to complete the experiment. So again, the student here has included a diagram. Strongly recommend that when you're doing the experiment, take a picture. Not enough to just put the picture there, you need to refer to it in the method. Labeling it makes it even better. Hand drawn, that's fine. If you can't get a picture, hand drawing what's there is fine. Just make sure it looks presentable and it's not a rushed piece of work. Okay, that covers most of the design components. You also need to have, so again, is a hand-drawn version that the student has included. You can do something very similar to that as well. Again, it looks like the students put effort in, they've labelled it, they've referred to it in the method. That's perfect. You also need to address your safety and ethics. Okay, so safety, whatever safety precautions you took in the experiment. Ethics, whatever you've done to ensure that the ethical obligation of the practical is withheld. So, for example, things like in this experiment, the student ensured that all yeast was disposed of in an ethical manner by passing it to the lab technician. Okay, safety can be done as a table again. You can talk about what the hazard is, what the risk level is, and what precautions are going to be taken to ensure safety is observed. Okay, then we get to the results. Okay. The results are, you've got tables, you've got graphs, you've got raw data, you've got manipulated data. I'd strongly recommend, so the results don't go to the word count. So if you've got good qualitative observations, throw them in. It's just going to strengthen your practical art. Okay, you want to include those qualitative observations. Okay, this, just an example too, this practical is up on the OneDrive if you want to read what the student's written. I'm not going to go through it. Qualitative observations, really important to help you with your discussion, and doesn't go to the word count. Why wouldn't you include them? The raw data, so it's being done to the correct format, which means he's got a table, he's got units, he's got headings up here. He's got everything done to the same amount of decimal places or the same amount of significant figures. So you can see this one's done to 3 significant figures for everything. For biology, it's enough to do every decimal point. So you could have gone 1.50, 3.50. It's enough to have just to 2 decimal places. You don't have to go to significant figures. Significant figures is fine though as well if you want to do that. Okay, that's the raw data. You then got, if you've done some process data like students here, you should always include a sample calculation. So this student here has worked out standard deviation, given me the formula of how they've worked out standard deviation, and then they've done one calculation to show how it was done while just including the rest of the data there. Okay, so if you're processing the data, which most people will, make sure you include that sample calculation. You're then going to graph the data. So graphing the data is, again, making sure you follow the correct formats. You've got a title, you've chosen the right graph, you've got your axes titles, your axes units. You don't have to include error bars. This student has, and that's fine, and it's a really good thing to include. It helps strengthen your discussion, but you only include them if you know how to do it. Okay, it's not enough to just go to an Excel document and say include error bars because they're all the same. As you can see with this student, the error bars are different because he's actually worked out how to do them. He's also got the equation of the line and the R² value. Again, you don't really need them, but it does help strengthen your discussion if you know how to talk about them. The things that are important is that your points are plotted. Like I said before, you've got your title, your axes titles, your units, data points are plotted, and you've got a line of best fit, an appropriate line of best fit. And that's where the R² value can help you there. The closer to 1 it is, the more efficient that line of best fit is for your data. Okay. Again, this student again has determined that one of these is potentially an outlier. He's explained why it's an outlier, and then he's removed it and regraphed the data again. Okay. So again, just summarizing results. Table has the correct format. Data is represented in an appropriate manner. All data is shown. Significant figures are correct. Graphs are drawn appropriately. Axes are labeled. Appropriate scale used. Title, size, and correct format. Okay. So everything there in results. It's easy to get an A+ for results as long as you're following those steps. Analysis is where we're now tearing apart these results to explain what's happening biologically. So you're looking at the results you've got, you're talking about your graph, you're talking about your tables, and you're physically stating, are these results expected? Are they unexpected? Why or why not? So if the results are expected, what's happening biologically? Why have we seen these results? What's happening in this experiment to get these results? If the results are unexpected, what could have potentially gone wrong? What's led these results to not be what we expected? Okay, all the time making sure you're bringing it back to what we've talked about in class or what we've talked about in your background theory. You're relating it to biological concepts. You're not just explaining what we see, so I wouldn't just go, as we can see, as the concentration of glucose increases, the graph starts to plateau. Yeah, well, it increases first and then it starts to plateau. That's not analysis. That's telling me what the graph does. Analysis is telling me biologically what's happening, why is it increasing, why is it plateauing, what's physically happening in this experiment. Okay, that's the analysis. So, explaining all the data points, expected or unexpected, and all these points for now, okay, that's the main thing in data analysis. Now, you then go through and you'd have an evaluation. Now, the evaluation can come before or after the conclusion. It doesn't matter. The correct scientific way of doing this would be you have your analysis, then you have your conclusion, then you have your evaluation. So that's how I'll talk about in this experiment. Again, if you do it in a different way, that's fine. Okay, so conclusion, basically, you're summing up the results that you found. Has the aim of the experiment been met? And was your hypothesis supported or not supported? You can never, with a year 12 especially, or year 11, you're never going to be able to prove your hypothesis correct. You've done one experiment, and that experiment has supported your hypothesis. It's not been proven correct. You've just found some data to support it. Okay, so your hypothesis is always supported or not supported. Okay, and that's basically what you're doing in your conclusion. So summing up the results, has the aim of the practical been met, and has your hypothesis been supported or not supported? You can extend that as well to talk about what's going to happen in further experiments, where the next possible steps could be. Okay, so for example, this student's written at the end of their conclusion, how the further testing with alternate apparatus is required to assess the true relationship between glucose concentrations on anaerobic respiration of yeast and the effect of osmosis. Okay, so they've indicated their results are just supporting the hypothesis, and this is not the be and all, and this is not the definite solution. Okay, he's indicated that there is further research to be done and given an idea of where that is to go. We then move on to our evaluation. Okay, so your evaluation is the rest of these points in the analysis here. So you're going to be talking about the data's reliability, precision, accuracy, and validity. Okay, reliability is how reliable are your results? Okay, has there been a lot of error in this experiment? Have you measured what, is the precision and accuracy good? Is the experiment valid? Is it measuring what it's supposed to be doing? So taking all that into account, are the results that you've obtained at the end of this experiment, are they reliable to answer the question that you set out at the beginning of the practical? Okay, that's reliability. Precision, okay, so precision talks about your results, okay. Do you have minimal scatter in your results? So you've done a few trials. Are all the trials fairly similar in their results? Okay. Accuracy is how accurate your results are, how close to the true values of those data the results actually are. So, when you've done the experiment, if you know what the value should have been, how close were you? Okay. If you don't know, you can still assume how accurate you were based on how many errors have taken place, etc. Okay, and lastly, you're looking at validity. So, at the end of the experiment, have you measured what you set out to measure? So, if your experiment was to look at the effects of enzyme concentration on lipase activity, okay, has your experiment that you've done, has that answered that question? The experiment that you've completed, has that looked at and seen results on how enzyme concentration affects lipase activity? That's whether it's valid or not. Okay, you're then going to talk about errors. So there's two types of errors. You've got systematic errors and you've got random errors. Okay, systematic errors are generally because of equipment. The errors in the equipment, so it might be incorrect calibration of equipment. It might be that the solutions you were using weren't made by you, and hence you don't know if they've been made correctly. It might be that the ruler is slightly damaged, or maybe you've got other things like that. Okay, so generally systematic errors are errors with the equipment, and what's going to you know a systematic error has occurred because it's moved the entire graph up or down. Okay, so it hasn't affected one data point, it's affected all data points because it was used throughout the entire experiment. Now, truthfully, you're never going to be able to identify if systematic error has actually occurred in your practical or not at a Year 12 level, because in order to do that, you'd have to repeat the experiment with different equipment. And you'd have to do that at least another 2 times. And that will just identify systematic error. It won't correct it, it will just identify it. Okay? So you can give the suggestion of what systematic errors might be, but you're never going to be able to say that they have occurred or they haven't occurred. You can just indicate this could be a potential source of systematic error. Random errors, on the other hand, and I think that students' random errors are up here. Okay, random errors are generally to do with human error. Okay, so matter something. So, for example, this student has talked about parallax error. Okay, so looking at eye level when they're measuring concentrations. Okay, fluctuation of water bath temperatures. Okay, air bubbles being present there. These are errors that are affecting one data point on the graph. Okay, so a systematic, if we looked at the back of these results over here, a systematic error would have moved the whole curve up or down. A random error would have moved one of these data points up or down. Now, I would strongly encourage you for random and systematic errors to be tying them to your accuracy, reliability, precision, validity, those type of things there. Okay. Lastly, you need to have a reference list. And if you go down to your reference list, Harvard referencing, that means in alphabetical order, following the correct school format, etc. Always include your bibliography at the end. Okay, that's how to write up a practical. Let me know if you in class if you want an extra hand with that. But hopefully this helps a little bit to supplement these 2 files that you have.